general measure theory. And also, the title is misleading because what we did so far was already general, in some sense that you don't need to add any new technique. So here we have the Lebesgue measure. So there is a way to understand that the general measure theory is exactly this theory, because if a measure is not made of countable many Dirac deltas, then by a measurable transformation or Borel transformation, you can always get back to this case. So essentially, well, this is a meta theorem, but actually can be very formal. If we prove something here, then you can translate back to the general measure case. So general measure theory, the starting point is as usual a measure space, or measurable space, let's say measure space.
Is there a name for Z theorem? Is there a name for Z theorem? There is a name for Z theorem to look it up.
The name?
Name, like the theorem that...
The background, yeah, well, there is a... Okay, I don't know, the theorem is even more delicate in the sense that you can transform any countable generated, measure space, complete measure space with a countable base into a subset of G delta subset of R. And then in a one-to-one way. And the transformation is Borel. At this point, you just, since you have a Borel function, you know that, you define the measure in R as, or well, vice versa. You can also require that essentially the measure so you decide the measure of a set in R as the measure of the counter space of the original counter. So I open a parenthesis for the question here. So the theorem was like this: you have a measure space with a distance, and then you can have a transformation, let's say capital G, into a subset with a G delta set of R with the topology of R, the standard distance. No? And this is well, the G delta, I think you can almost make it continuous. I have to check, but more or less you can make this continuous. And actually you can require that you have a measure here, a Borel measure. You can build G in order that, well, here you have a natural measure over here, because the G delta is one-to-one. So if I give it E containing R, I define the measure M of E as the measure mean of the counter image. But then you can require that M is really equal to the Lebesgue. If, and only if, well, there is one case you can do that. So if mi is a Dirac delta, but there is no way. Here you have a Dirac delta, because one point goes to one point. And so the requirement is that mi is not, has no, let's say, discrete path. So mi has no discrete path means that there's no Dirac deltas. So one way of rephrasing it is that the measures, they don't see dimensions. So whenever you have just a program in measure theory, you can forget about dimensions. I don't remember how to, but because there are several variations depending exactly what you want. But in philosophy, I think this is correct. What I wrote down is correct. So let's do here. So measure space. Okay, here, what was the measure space we built? Was R. The measurable set, which are the Lebesgue measurable sets. And then we have the measure M. So this is the space. This one is the Lebesgue measurable set. And remember that RL contains B, the Borel set. So it's a large family of sets. And this is the Lebesgue measure, which is perfectly characterized once I define should be a measure on the Borel set by the measure or an interval is equal to the length of the interval. No? So here I identify everything. So now in general space, okay, you have X, which can be RD, and for us the Portuguese is RD, but the theory does not matter. Then I need to give a sigma algebra. And the most important is the Borel. And then I need to give a measure mean. And actually there is one property which I need to consider there, that I have that naturally. So that me is finite over compact sets by definition, because a compact set has finite length. So let's say remark, me is finite over compact set. So and here, okay, if I'm in RD, I just require me is finite over compact set, and that is fine. So in a general space, however, when the one thing is that me is finite over compact set means also that me is as the sum of measures which are finite, because you take just every interval n plus 1, restrict n to these intervals, and then me is fine. So I have to add something there which usually is correct. In RD is exactly this one. In general space you need to add something a little bit more strange. So let's say me is so there exist, let's say, properties that you require. There exist xn contained in x, the union over xn is equal to x, and me rest of xn is less than plus infinity. And this property is called sigma finite. So this is just because we like to work with measures which are finite. Why? You have any idea why in all the theory we have seen here
this
we use the finite?
Just only for one xn or
for all?
For one?
For all xn. Otherwise you take a point for the empty set.
Because in the theory
Subadditivity? Because of subadditivity we have
for additivity, yes, but that's works for plus infinity, but
because in the theory of a big measure we were always reducing everything to intervals, and we were using always that the length of the interval is b minus a, which is finite. So
yes, every time you have to remove a small set, is small set because the ambient set has finite measure. So think Egorov, or well, if you can think also when we use the Lebesgue theorem, the uniform boundness theorem. Well, you have an integral which is finite. Because of plus infinity is always a problem. You have only one part of the inequality. The subadditivity is fine plus infinity, but once you want the additivity, so you want to have to control something because the sum is finite, you need the finite, otherwise you don't control. And also think, for example, when the intersection of countably many sets, you need at least one as finite measure. So in some sense, if you don't have this guy here, well, you got into trouble, and also you have questions which cannot be decided. So it's not really something that the theory is more complicated. It's really the theory requires an approach to logic. Okay, so sigma. So in RD, equivalent is equivalent measure of any ball around values n is less than 10. Okay, so usually all the measures are satisfied this one, otherwise you have here in that degenerate case. There are some degenerate cases. I hope I have this. Okay, so any doubt about the definitions here?
Anyone?
Doubt? So you are fine, you know what is a sigma algebra of sets, you know what is mean?
About me, what is for conditions for you?
Yeah, exactly. I mean, exactly. If you know, are fine with the
It's
conditions.
for like to in first lecture is empty set is 0 and subadditivity just
Additivity. If it has a measure, is sigma additivity on the sigma algebra.
And what about invariance? This was crucial in the big measures.
That case false.
This what?
In general, is false. If the Lebesgue measure gives, so the only invariant measure on RD is the Lebesgue measure. But in general, it's false. Okay, so let's build a strange measure. So how to build a measure? So the procedure is the same.
We define an outer measure on
Yes.
X and use Caratadori.
Exactly.
trick.
To build a measure, okay, you start with a measure which gives, with a function which gives values to, well, for example, at the end of algebra you need to have, I think, a semi-ring and something like that, but we don't want to enter into, because, okay, I have to read. I never trust this. So you have a function on a family. So typically we want to put on the open, let's say, on a family of sets. Let's say this family is F. Let's say G. Then you define the measure out star is of any set E is the infimum of the sum of the covering. So let's say if you have a function, say capital F of well, some set let's say AI, where AI is the family and the union of AI cover the set. Okay. And then, okay, as usual, you define the measurable sets. So this is an outer measure. And then, okay, the measurable sets are well, the ones such that they satisfy the standard. So the mi star of any set A is equal to mi star A minus E, mi star A intersection E. So the procedure is the same one. So the difficulty here is to prove that the measurable set belongs to some class. So you remember here the difficulty was once you have the Lebesgue measurable set, I want to have this inclusion. So I want for sure to measure the intervals. Okay, so let's see some example here. Okay, the first case is that since we want to build the Lebesgue measure, so what do you do? So here we have intervals, but now I want to build the Lebesgue measure. In RB.
Array. You need to take array, volume or area you need to take?
Volume array, yes, it's fine. So what I measured, which is my family there?
Boxes.
Boxes, whatever I define. Also balls is fine. So I have a measure, so let's say boxes is fine. Boxes is nicer because it's easy to find. So boxes, so let's say this is the length Li. So I define that, so let's say f of the boxes is the product of its length. Then I obtain, in some sense, the outer measure of any set. And, well, okay, and this one, okay, we don't have time to prove, but actually the line is very close to this set, if you remember here, we have to prove that the boxes are measurable. Because the boxes, if you know that the boxes are measurable, you know that the Lebesgue set, that the measurable set is a sigma algebra. Boxes clearly generate the topology. So open sets are measurable, and then porous sets are measurable. Okay, so but the procedure is very close. Remember, you take a box, and then you need to have a covering such that essentially two disjoint covering of the box and outside the box. You remember, it was like this one. So inside the box, if you intersect any box here with this box, is again a box. So it's fine. Outside is not the case, but actually remember, we just move a little bit. So essentially we take a small neighborhood, and then outside a covering, still a covering with boxes, and then the measure here is as small as I want. That was more or less the... Okay, and let's see another example. So I can define the following. So given E and given delta, I define H delta of E as the infimum, let's say H delta alpha, and let's say alpha fixed.
How slope measure? How slope measure?
Yeah, yes. I'm doing that. So it's the infimum of the sum. Okay, here I need to have a constant. We forget about the constant so far. So Ri to the alpha, where Ri are the radius of the ball, center at some point, they cover my set P. So let's make the drawing. This is E. I take a covering. Okay, each one has its own radius, centered in xi, and then I measure the radius to some power alpha. And sorry, and here I say that Ri, however, are less than delta. So the delta enter like this. I cover the setting with balls less than delta. And then I take the minimum of this covering. So now, when delta goes to 0, this is increasing because I restrict the set of balls I can choose.
But because we are taking the infimum, isn't it true that if I don't put the restriction that Ri is less than delta,
then I take a large ball and B is the length. Because, for example, imagine that alpha is equal to 0, so it's the number of balls. And then one ball, but actually it's not, the 0 we will see. So now, when delta goes to 0 increases, so define H alpha, so this is, at the end, it's already a measure.
Sorry, what is the condition for alpha positive or no?
Yes, sorry. Yes, alpha is greater than 0. Is the lim for delta that tends to 0 of these quantities. Okay, now let's work just for fun. So alpha equal to 0. This is the number of balls. Then H del alpha delta of E is the number of balls. The minimal number of balls covering. So when delta goes to 0, essentially it becomes the number of points. So H0 is the number of points. So there's the cardinality. Then you can prove essentially that as I wrote there, HD alpha is equal to D is equal to, well, it's almost the Lebesgue measure, because here I didn't put the constant, should be the constant here. Because if you have a ball, the measure of the ball should be the same. No? But look, if alpha is equal to D, is the same definition as the Lebesgue measure, but for the omega D, the volume of the unit sphere. So it's the volume of the unit sphere. So it's 1 over the volume of the unit sphere. This is the volume unit sphere. The measure of D. You can prove that if alpha is greater than D, H alpha is equal to 0. And well, now there is the reasoning about dimension. In some sense, if it is finite for some alpha, then it's 0 for alpha greater than that alpha bar, and plus infinity alpha. So you have essentially, you can define the Hausdorff dimension and so on. But you see, the procedure is always like this one. So I define what is the outer measure of a set. So I have a family of sets, and then I define how to measure them, and then I do the standard calculation. Okay, so far so good. Okay. So after we have a measure, we have all the theorem. So let's say here I remove. So remember, here we have all the various theorems that we know we can use. So the limit theorems are, for example, the sigma additivity, so the measure of a union, so M of the union of these joint sets is the sum. Then we have the other theorem that the intersection, so if the one set has finite measure, let's say L1 is less than plus infinity, the measure of the intersection, and if I is a decreasing family, is equal to the limit of the measure of the I. Okay? Then what we prove essentially, after this guy we have the principle, no? the regularities principle. But by definition we have that if a measure, so there exists a G delta set such that, so for all E there exists a G delta set such that E is contained in G delta, and the measure of, let's say, G delta minus E is equal to 0, or they have the same measure.
0 or smaller than some epsilon?
No, if this G delta is 0, if it's open, is the same. If this G delta set is the section open, then you use this thing to say that they should go to 0. Then we have the other regularity. It was losing or ego or whatever you. So if Fn converges to F, well, and Fn are measurable in a set of finite measure, then for all epsilon there exists a subset, a compact set, let's say subset E of finite measure contained in E, such that the measure of E minus this set is less than epsilon, and Fn converges to F uniformly in K epsilon. Then we have the losing theorem. So essentially, if F is a measurable, then there exists, for all epsilon, there exists a continuous function, G continuous, such that G is different than F, the measure is less than epsilon. Okay, then we have the limit theorems. So, for example, so essentially the most important is Φ2. Well, we have the monotone convergence, Fn greater or equal than 0 increasing to F. Then the limit, everything is measurable, no? The integral of Fn is equal to the integral of the limit. So it's F. If Fn greater or equal than 0 doesn't matter, then the integral of the limit less or equal to the limit of the integrals. And then we have, well, actually there are several versions. Let's take this guy. So Fn less or equal than G, Fn converges to F, and this is now integrable. Then the integral of Fn converges to the integral of F. Then we have some weak version for uniform integral E tightness. Okay, now everything, if we are in the Borel case, because I need to be sure that G delta sets are measurable, is translated just replacing the, you see the is already written in something that you don't need to work, no? I mean you don't R appears here, you have to replace RD, but for the rest it's the same. Okay. As we say in practice mutatis, so which means after you change what you need to change, which is a tautology. Okay, however, I cheated you a little bit. What does it mean there to have a function which is measurable? The same. Open sets is in the sigma algebra, let's say.
Pre-inverse of measurable set is measurable.
Inverse of measurable set is not a good question because you don't have a measure in the end space. The measure is in the let's say in the starting place, starting space, not in the end space, in the domain, not in the range.
But in general, mu is a function into reals, right?
F or me?
Mu.
Me is a function with real value, yes.
So we have a measure, the big measure on R. So
We have a measure on
R.
y. This is a function from
Yes, but we have already constructed the big measure on R. So I mean, why don't we define it to be measurable if the pre-image of every big measurable set is in the sigma algebra.
but then you get trouble because we have examples now that counter image of set of measure 0 which are not measurable in L, they have positive measure. And so I think that no, it's not, because you don't need any measure there. I mean, the definition is just counter image of open set is measurable. The counter image of measurable set is too large, no, to be measured, because you have examples of functions that you want to integrate whose the counter image of set of measure 0 is non-measurable. And then you throw out this, and at the end you get just for only, I believe, only the Lipschitz functions. It's too strict. If you say that the counter image of too many sets should be measurable, is worse than saying that the counter image of small set or a smaller family of sets. So you just need at the end I think you get only too few functions. While you can just, because you don't need a measure at the end you just sum up. You don't need to compute the measure of the image of a set. You just need to sum up the level sets, which is different. And actually, at the end, what you said is not false, but is more complicated. If I give you a function, I define what is the image measure, and then the counter image of any measurable set with respect to this image measure is measured. That's fine, but it's more complicated. And another thing is here, let's see, what is the integral?
We start with positive, maybe approximate by simple functions.
Exactly, it's always the same. For simple function, it's easy. For simple function is exactly what we did here. But the only variation is that instead of having measure of subset of intervals, here you have measure of subset of balls. But then it's fine. You just add up and then you pass to the limit. For positive, then you find when it is integrable, when the positive and the negative part are final integrals. So everything is the same. So you are fine with this guy. I know that it's not the best way, but I have only 1 hour and a half. And I think also you can review that all the theory in R works in some sense flawlessly. No, you just go. Okay, and now we start with something new, however, because so far so good. Let's see what was the first. I want to do. So there are 3 theorems here, very important. Which was the first? Okay, sign and measure. So here we do always, this part is an example. So here you define the following functional sets is equal to the integral over E of a function gm, and G is just L1, but it's not positive or negative. Okay, let's see the properties here.
0.
0.
The EIs are disjoint, then the sum.
Measurable, they're measurable in this joint, no? This is
Sum.
the sum. And now, plus infinity or not?
It depends on G.
Is in L1. This means that the integral of modulus of G
Okay.
what do you think?
Yeah, but every sum is less than infinity, but it could be that the sum of them is infinity.
But,
This could be an exercise. This could be an exercise in the exam. Prove that the integral of the sum of any partition for G in L1 is less, the modulus is less than plus infinity. Okay, we write. Do you mind if we write? Okay, I write. Then you stop me, yes I see, and then you finish.
What, can you repeat what we are going to prove?
We are going to prove that is this sum finite or not if the I are disjoint. Let's try it. You see? You see?
Yes, we enter the modulus and that each one is finite and all of them represents
This is the less or equal than the integral of G.
the
Less than plus infinity because G is in L1. Okay? Okay, with this example now I can define what is a signed measure. So signed measure is no more than that. So, okay, you have X with a sigma algebra. Let's take Borel at the end. This is the Borel sigma. Because at the end we work always with Borel. Then mi is signed measure. Okay. I disjoint and contained in the Borel is the sum of the measure. So, do you think that what I wrote down there, the sum of the series is converging absolutely? Then do you think is now a consequence of the definitions, or it just holds for the, well, of course, if I put the rest this way, it's clear what is the answer. Is a consequence, is just holds for that particular case. Okay. So the sum should converge for any disjoint partition. So take only the terms which are positive. It's a disjoint partition. Okay? So, sorry, I forgot to say, and the ni of E is in R for any E. Just the real value, never takes plus infinity or minus infinity. So if you take just the sum of the positive, then it means that its sum is finite. The sum of the negative is finite. So it cannot be plus infinity. It means that the series converges, absolutely. So what is now the basic theorem? Let's see a little bit. So we know, so then properties. The sum of the absolute values converges. In particular, the Lebesgue measure is not a signed measure, because the Lebesgue measure of R is plus infinity. Okay, so we have this guy, and now, so do you have any idea how to rewrite this? So if you have a function, you can say the positive and the negative part. Do you have an idea how to rewrite this into a positive and negative measure? The difference of two positive measures.
Yes, G plus G minus.
Yes. So there exists a set. Now the difficulty is the following. So there exists a set, let's say A, such that ni plus of E is equal to ni plus of E intersection A, sorry, A, and ni minus of A is equal to 0. So before writing, do you understand what I'm doing here? Let's take a function. I can say the positive part is the function restricted to the set where it is positive. And vice versa. The negative part is the function restricted to the set where it is negative. So here is the same. There exists a set which is A such that ni restricted to A, which is this formula, is always positive. And the negative part is in the complement. So you see how to, in this case, work which are the two sets? Or here, you see immediately, no? Which are the two sets? That's G. This is G.
Sorry, this is for every E?
For every E, yes.
It means that the measure of negative part is finite, it means, or something.
The negative part is finite, but is not on this set. Okay, so which would be the set E in this case? The set A.
This one.
It's only this set, no? Because the integral of G plus is clearly the integral of E intersection where G is greater than 0. It's equal. So it's written here. And clearly the integral of G minus where the set G greater than 0 is equal to 0, because G minus is 0. Okay, so this is the Hahn decomposition theorem. Ni is a signed measure. Jordan added, no, I think don't remember which one. What is it? This maybe is Jordan. Because there are two versions. Now, one is that you can write like a sum, the other is that each element of the sum is the measure restricted to a set. So there exists, let's say, A, let's say, which depends on, let's say A plus, such that this is the model, such that Ni is written like, so Ni of a set is Ni of a set intersection A plus Ni of a set intersect minus A plus. This is obvious. And this quantity is greater or equal than 0, and this quantity is less or equal than 0 for all E. So you have the part where the measure is positive and the part where the measure is negative. It's like for functions. Okay, the theorem tells you that you can do that. So every time you have a signed measure, well, it's just the difference of two finite positive measures. And they live in different parts of the space. So it's no problem. If I know how to do that, to handle the positive. Okay. Now, let's go on with this example. So this example tells me so essentially it tells me that the measure of a set is the integral over that set of a function which is n1. So then I have the following properties. If the measure of E is equal to 0, then is equal to 0. Is that true? Yeah. Yes. Because well, how to prove it? This can be prove that is false. How to prove it for you?
Because J is almost equal to 0. It means that in the E. Because
can't we take the modulus and apply the triangle inequality, and then we say that the integral of modulus G is less than or equal to measure of E?
There are several ways. Okay, let's see. Let's start with by definition. Let's apply the definition of it.
Definition?
It.
Okay.
That's the integral G times the indicator.
Simple function.
Okay, first we have take positive or negative. The G is in N1 is a sum, so well, you just need to prove it for the positive, no? Because if it is 0 for the positive, then the negative is 0, and 0 minus 0 is 0. Okay? Positive. And now you are in business. So you start with simple functions. Because for positive we have the monotone convergent theorem. So we don't need to assume a finiteness. For simple function, why is that so?
Because in this case, we can apply
This is 0, so the M of any level set restricted to E is 0. And then you apply monotone convergent theorem. Or, let's use losing. It's free, it's define what you want. Clearly losing is a big gun. Because I can start from the definition, no? But actually losing, I can use losing. It's up to you. So in the written exam, the questions are open. You can choose the line you prefer. The only thing should be logical. Because the problem with the exam like this one is that you can write also things which are illogical. So let's say losing. So G is continuous up to, well, in this case, since I'm in L1, I can prove that G is continuous up to a set whose integral of G on that set is small as I want. Or you can say any approximation. I know that there is a theorem which tells me that there exists a simple function such that G minus the simplest function is modulus, its integral is small. So let's say this is epsilon. Now, the integral of a function which is bounded over a set which is measure 0, I use the monotonicity is less or equal to the supremum times 0. So I have that this is as small as I want. Okay? So let's rewrite this assumption here. Okay, I can take near positive because I have this decomposition. So if I prove something for positive, I prove something for sign measure, let's take the difference. Which reads as mi is absolutely continuous with respect to mi if for all e mi e equal to 0 implies mi e equal to 0. So it's exactly that statement. Now, theorem, Radon-Nikodym theorem, very important. So here we have always measures which are sigma finite, remember. Or here let's take finite measures. So let's say I need to draw this to be finite. And let's say, well, let's have also mi finite, which means that it's finite on any compact set, or, well, it means that in R is a finite on any ball. Then, is measurable. Now I have to specify. So this means that the integral of G is greater or equal than 0. Yeah, because I assume positive set, positive function. Such that so that example is the example. It's not that you can have more complicated situations. No. So this condition is really equivalent to this condition. So you know how to compute this integral?
Can simple functions?
Yes, exactly. I just wanted to be sure. So now there exists an improvement.
I think the order is reversed, because here we integrate with respect to the measure m, and the premise is that the measure of e with respect to m is 0. But here the role is reversed.
What?
Because here you say that
in general?
Yeah, but here we integrate with respect to mu.
So here I'm replacing m with me.
Yes.
So m equal to 0 becomes me equal to 0,
Okay. Ah.
and then it's okay.
Yeah.
So the second part, let's say theorem, which is again about detail. In general, okay. In general, ni of e is equal to the integral for n. If I don't assume this guy, well, okay, then I explain now. Is perpendicular, is orthogonal to me. Okay, so let's see now. I have to explain what is orthogonal. Let ni equal to, let's say, the Lebesgue measure, so the measure of E is the Lebesgue measure of E plus, or let's say, plus delta in 0. So here it means, sorry, it is the delta of 0 of E. So it is 1 when E is 0 or not. Can I write this function as an integral of an N1 function? So the question is the following. Can I write the measure delta 0 of E, which is equal to 1, 0 is in E, 0, 0 does not belong to it, as the integral of some h, and h is in A1?
No, because if I just remove a point from the set, the measure doesn't change and
Exactly.
yeah, it doesn't change.
And so it means, so you notice the following. There exists a set, let's say A, such that the measure of A is equal to 0, and for all E, delta 0 of E is equal to delta 0 of A intersection E. What is the set? Exactly, you remove a set of measure 0 and then everything is on that set. So what is the, in this example, what is the set? Well, there are several names, gives me one. What is the set such that this property holds? So all the measure is concentrated on that set.
Take any point except 0, right?
No, take just 0. You not remove the A, you just which set you have to keep.
Yes.
Just 0. So A equal to 0. So orthogonal means exactly this property. Definition. Ni is orthogonal to me if there exists A such that the mi of A is equal to 0, so it is a set which is negligible for me, but for any set, the measure is equal to the measure restricted to E. So essentially it is equivalent to say that mi of the complement is equal to 0. Or mi of the complement is equal to 0. So everything is concentrated on that set. So So the general theorem tells you that, well, this holds in general. So any measure can be decomposed like a part which is absolutely continuous and the part which is orthogonal. So let's see another example here. Take 2 points. So let's say μ1, no, μ and μ of E is equal to the integral over EHM. Can you compute what are the 2 decompositions there? So I want to write and now I need another letter, let's say F okay.
Have the sum and have the minus? Have the sum and have the difference?
There, the half is, no, would be fine, but it's not the case. But okay, yes, you have to do some operation with G and H. Okay, so let me go. So I write neo E is equal. Now I define for E intersection H different than 0. E intersection H equal to 0 of now this is me. This is really me because when H is equal to 0, this is always so it's a function, let's say F me plus, and this is the orthogonal part because it's restricted to the set which has 0 measure because H is equal to 0. And F is equal to G over H for H different than 0. Then I don't need to define set equal to 0 here. Simply because you can observe when H is equal to 0, the integral is 0. So that is the part where is the set A where the orthogonal part lives. So I just remove it. In the rest, I just do the ratio. Last part, I'm sorry, and then it's finished. This is just for your knowledge. Last part. Last part, at the end, I need to compute things. So it's very nice that I have all this theory. And so I build the Lebesgue measure in RD, and I'm very happy, but at the end I have to compute. But the procedure is there. So let's cancel this guy. So for example, you can compute. For example, the integral of e to the minus x squared, modulus of x squared, with respect to the Lebesgue measure in, so the x1 dx2, let's say x squared plus y squared dx dy in R2. Okay, I have this very nice theory, I can start it now. But at the end I need to compute it. And so,
P. P.
Is P, yes, I have many methods, a change of variables and whatever. And when you do the change of variables, so you compute like for the Riemann integral, but now we are in the, so the change of variable was one of the didn't have time to see the exercise a little bit, but so that the key point is that you iterate integrals. You integrate first one direction. So the key point integrals. So when you compute something which is dx dy is a double integral, you integrate in dx or dy and then integrate this integral in dy. So we need to do, this is the last missing part, and then basically we are fine. This is the last missing part in the computation. So there are two theorems here, because you know that you can compute integrals only if a function is L1, in some sense. And then I'm in trouble. So how to verify that the function here is in L1? So I need to say that, oh, if this integral is measured less than plus infinity with the modulus, then this integral is less than plus infinity for almost every y, and this function is integral in y and is finite. And then I need to say, well, once I can compute both integrals, they are equal. So let me say there are two parts. So iterated integrals. Remember, for Lebesgue, I need to be sure that I can give a value. And then I can, once I have the value, I can say the value is equal. Because maybe it may happen that I can give a value here, but I cannot give the value there. Or vice versa. This is a value, but I cannot iterate. You understand, no? There are 2 points. You remember, the Lebesgue theory, for positive, certainly you believe it's true. But then, for it is not positive, how to do that? So I need to do the 2 parts. So, first step, verify the integrability condition. Condition, well, let's say there is only one, the integral of the modulus. And so the second step, so it's compare the integral, the double integral, or the integral in the product space with the iterator. Integral. So I have the following, the 2 steps, no? Because it's not obvious that I can compute the quantities. So there are 2 theorems about it. The first theorem is Tonelli. Actually, at the end, you say Fubini, Tonelli, just Fubini. So, if it is equivalent, let's say they are equivalent. The integral, the double integral of f, let's say xy, we are always finite measure. So let's say, and here I take the 2. It holds for any space, no? But let's say L2. But it holds for any space, LD, or even me times me. Then maybe if I have time, I explain what does it mean. less than plus infinity to, so the iterated integrals. The integral fx, so f xy is integrable say L1 almost every y. For almost every y, this function can be integrated in x. And y, the integral of f, now in the Lebesgue measure, dx, is integrable in y. This is the iterated integral. So how to prove that clearly the easy part, so the difficult part is to compute this directly. That's much easier. So it tells you that if you can integrate for almost every y along parallel line to the axis, to the x-axis. And then that function can be integrated vertically and the integral is finite, you are fine that the function belongs to L1. So this is how to verify that the function is in L1.
Sorry again, if
Okay.
horizontally,
I'm giving you a function, so let's say a set, which is the same. How to say that this set has finite measure? Either compute, or I just do the following. I compute the measure of each of these slices. I can do also vertically, you know, but let's start. And then I integrate, so this is a function. So let's say I get the function which is the length, which depends on y, is equal to the measure of the set E intersection y. Let's say should be the length, the line at y. Okay, this is the function. I can compute it. And now I integrate this length, this measure, in dy. So essentially I adapt. And the theorem tells that if this integral is less than plus infinity, then the measure, the Lebesgue measure in 2 dimensions of this guy, of E, is less than plus infinity. Just to check that the function is L1. The second tells you that the integrals are the same. So this is step 1. Second step, which is Fubini theorem. If f is L1 of the double measure, then the integral of f is equal to the iterated integral. So you see how to use these 2 theorems. Well, one is used to prove that the function can be integrated, and it clearly should be like that. It cannot be that on one side is less than plus infinity, on the other you get something strange, or vice versa. It's like that if you are in sigma finite space, otherwise it's false. And then once you know that you can compute the 2 integrals, so if you can compute one integral, you can compute the other, then the second theorem tells you, well, and then they are equal. Because for the theory, you always need to be sure you can compute the integral. No? That's why. So the first step is always to be sure. So let's see just to some stupid thing here, just to have the feeling of what's going on. So one is, what is a product measure? just for fun. If I'm giving you a measure, is a measure finite on R. What is the product?
We define it on the rectangles in the product space as the product of the measures of.
How do you
If I have a set A and B in X, in the sigma algebra, I define the product. Yeah.
What is the measure of this set? If this is a,
U of,
say,
this
it is the interval 1 and this is the interval 2.
U of I1 multiplied by U of I2.
Exactly. So in this way I define
This looks
Outer
like
measure on the.
an outer measure and then I prove that it's a fine of Borel sets. If the original me is fine of Borel sets. So you see, this is the product, how to build a product measure. It just is naturally defined on sets which are product of sets. And then you have a standard procedure which allows you to extend to all the sigma algebra. Fine? So let's do something strange here. Okay, I do the following partition. Sorry, this one goes up to here. This one goes up to here. Goes up to here. Okay, so now I color the thing. This goes on, no? And then okay, now I have to put values. This is it's a function which I just assume a constant value. So let's put it here. 1. Okay, the values are 1, and this is 1/2, 1/4, 1/2, 1/4, and so on, and go to 0. And here I put -2.
what is -2?
Hmm?
-2.
The values, yes, -2. Sorry, -2. I just colored too much. So let's put here 2, or let's say -2. So I put here is 4. Okay, sorry, let me increase this one. It doesn't matter, it comes to 0. So, okay, -2 is fine. So let's put this 8, -16. And here I put 16 times 4. So let's say here is 4 times 16. And here is 2 times the value above. You understand, no? With a minus. So essentially, here I double the value with the minus and multiply by -2, and here I multiply by 4, by -4. -2, -4, -2, -4. In this case, I clearly, as a procedure, will define the function of all rectangles. Is the functional 1? Okay, let's apply it to Tonelli. Compute the iterated integrals. If you get something strange. So the integral here is 1, and here I have 2, so let's say, well, at the end, you see, the integral here is 4 times that is integral. So the values are 4 times the values here, when I go here. But the size is half. So the integral is twice. So it's 1, 2, 4, and then I go on. So the sum is plus infinity. It's not the 1. Let's compute we try to apply Fubini. So Tonelli says that is not a 1. Let's apply Fubini. You see, this length is half that this length. So the integral vertically is always 0. It's because it's 1 with length 1/2, so 1/2, minus 2 with length 1/4, minus 1/2. And you see, I always constructed the procedure in order to have that the vertical integral is 0. And so I get that if I integrate it vertically and then horizontally, I get 0. Let's integrate horizontally. So minus 2 with length 1/2 plus 8 with length 1/4, I get always. So it's 8. So it's 2 minus 1. So 1. 1, 1. If you go on, I get always 1. So the integral is plus infinity. So the integral here is 0, the integral there is plus infinity, the integral on this one cannot be computed because it's not in L1. You see that? The theorem has sharp. Okay, I think this is the end of the story. And so, just one question: this is always equal also to the other one, no? I integrate first in the y and then I integrate in the x. So this is the end of the story. So see you on Friday for some exercises like in the examination. Questions? This part will not be rectified. The exam will not cover this part, of course. It's too fast. At least you know you can do everything in RD, and then you have these 3 theorems, which are some additional tools.
On which other spaces we can construct measures? On which other spaces we can construct measures? We are talking about RD.
Yeah.
Which other?
The metric space, the theory works flawlessly in metric space with a countable generated topology, countable base of balls. The theory works the same.
Also depends on the topology.
Well, in a metric space with a separable topology, no. It's the same. The theory is just the same. Changes because the measure at the end you can go back to have everything in R is this in a G delta set of R. So nothing changes. Well, the product really changes because of the product. The space is metric space with a separable topology. That's it. Then it works.
Sorry, what is a general measure? Actually, for example, for Lebesgue measure, Hausdorff measure is general. For Lebesgue measure, particular case of Hausdorff measures.
No, but there is no answer to it because you can always have what do you mean, a general formula for any measure.
Yes, for example, we have a lot of measures for variables.
Well, you can always think that everything is like the counter image of the Lebesgue measure by a Borel function. And then, okay, yes, everything is like that. So, for example, the Dirac delta is the following function. Yeah, but I think it's not really useful. There is no simple formula. So what you can say, or every measure is the Lebesgue measure. So let's say you take Lebesgue, so the measure m on 0, 1. And you want to have a delta here, well, you take the constant function, and then you define, define the measure in here. So let's say here is a varying function f. You define for any set E, measure of E is equal to the Lebesgue measure of the counter image. You can always take this to be the Lebesgue measure, but then you let F varies. It's always like that. But Hausdorff measure is likely critical, because Hausdorff measure in RD is not a sigma finite measure. Indeed, you never see, essentially, you never use the Hausdorff measure just for compute the dimension. It's always the Hausdorff measure, so if alpha is less than D, sorry, yes, then H alpha is not sigma finite. So everything we just said is not working. But usually what happens is that H alpha, well, H alpha is a particular, so something is working, but not all. So usually, you take H alpha restricted to a set A, where H alpha of A is less than plus infinity. And now it's a finite measure. You never take a set, H alpha is bad, because so the counting measure is plus infinity. That's a particular case, the counting measure, but usually it's always plus infinity, but for sets which are finite. And so you just consider that case. Okay? So, see you on Friday for the last. We are on holiday.